Hello and welcome to day 4 of Unit 5. Today we're going to be talking about definite integrals. It's just a brief introduction to definite integrals. Basically, what we have is our definition of the area under the curve. And now, if we say that the definition of the definite integral, the integral from a to b of f of x of dx, is equal to that limit of Riemann sums, that definition of area under the curve, it now becomes plain to see that what the integral represents is the area under a curve. Okay, so we define the integral of f of x from a to b. Those are called our limits of integration. Okay. Limits of integration. So the integral from a to b of f of x is equal to the Riemann sum, or the area under the curve. So looking at just this guy here, the area under the curve from a to b would be from a to b and this is what's called area above the curve. And since that area is below the x-axis, it'll actually get calculated as negative area. So the total area from a to b would be the absolute value of the area from a to this point minus that area plus that area. But if you were to calculate the integral from a to b, the negative area would get taken into account, and you wouldn't have to really do anything special about that. So let's look at this first example here. Express the definite integral from 1 to 5 of 9x dx as the limit of Riemann sum. So basically we want to write this using the definition. So this is sort of like a problem before, but the information is given to us in a new format. My interval is now represented by the limits of integration, 1 to 5. Okay, so we can calculate my delta x as 5 minus 1 divided by, remember when we're doing the limit of a Riemann sum, the number of subintervals is approaching infinity. So that'll be n. Okay, and then let's see, x sub k star is, let's just say we start at 1 and we add 4 over n every k. Okay. Then f of x sub k star is 9 times 1 plus 4 over n k. So my limit as n goes to infinity is k equals 1 to n of 9 plus 36 over n k delta x. And let's do this just to be clear. Okay. No need to evaluate this. It's not what I'm concerned about with this problem. I just wanted you to write or express this as a limit of Riemann sums. So, and that would be it. Okay. All right, so on, I believe it's page 357, there are a few theorems that list some properties of integrals. Okay, and we're going to take a look at a few of the applications of those properties here. Basically, you can scale an integral, you can add an integral, and you can subtract integrals. So remember that the integral of a function represents its area underneath the curve. Okay? So the integral of f from a to b is just going to be the area under the curve from a to b, which is 7. Easy. F of x, or the integral of f of x from a to c. Now from a to c, one of the properties of integrals says that I can break this up into the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Okay. Well, the integral from a to b was 7, and the integral from b to c, the area is 3, but the integral from b to c is -3. So we get 4. Okay. Now, the integral from d to b. So I can, the first two examples had me integrating from left to right. But this is asking me to integrate from right to left. Well, one of the properties of integrals says that I can switch these bounds, but I have to multiply by a negative. Okay? So I have to say negative b to d of f of x dx. Now I can just integrate like I would normally. And I can either split these up into two integrals, or I can note that this is going to be a -3 plus 2. Don't forget that negative. Okay. So a -3 plus 2 is -1. Minus 1, or times -1, is a positive 1. Okay. Now another way to think about that is that when you integrate in the opposite direction, you get the opposite magnitude. You get the opposite sign of the integral. So the integral from d to c is -2. And the integral from c to b is +3. So a -2 and a +3 gives me the +1. Okay. It's just another way to think about it. Integrating from right to left, you get the negative value of what you typically would have gotten. Positive area above the x-axis, negative area below, but you get the opposite of that area if you integrate from right to left, as opposed to left to right. So the definition of definite integral that we've seen so far is a limit of Riemann sums. Okay, and remember the Riemann sum involved dividing up some interval into subintervals, and then taking that number of subintervals and increasing it to infinity, which makes the widths smaller and smaller and smaller, decreasing the area, and then approximating or giving the exact value of the area underneath the curve. So that definition of definite integral uses the area model. There is another definition of integral, or definite integral, that really is a little bit more straightforward and represents the sum of y, the continuous y values, as in if we've already taken the limit as n goes to infinity. Okay, but it can be written this way, and the way that I know that this differs from the previous example is that the delta x is there. Okay, in the other example, delta x is your end minus start divided by number of subintervals, and so you end up with an n in here, but we don't have that. We literally have, or explicitly have, the function at various values of I times the width of each of those subintervals. Well, that's just d. That's going to be our dx. Okay. And this becomes my integral sign. Okay. So to write this as a definite integral, it's the integral of x cubed plus x sine x dx from 0 to pi. And that came from the interval that was given to me. Okay. The interval would be given to you in this instance. It could be the case that you were asked to go from a limit to a definite integral where you were given the definition of area under the curve, and you would have to solve basically or figure out what your limits of integration were by knowing what the delta x was. Okay. But this is our answer. Okay, oftentimes it's beneficial to be able to interpret an integral as a geometric representation of just area. And that happens typically when we're integrating linear functions. And sometimes it can be quicker to think about this as an area as opposed to actually calculating the definite integral by using the fundamental theorem of calculus, which is something that we'll get to next in the next lesson. So what this function looks like is just a line. It's got a y-intercept of 1, and it's got a slope of 2. Okay. And we could keep going, we could keep doing this, but there's not really any need. Oops, kind of missed the mark there. Okay. Because we only want to integrate from 1 to 3. So from 1 to 3. So this is the area we're looking for. Okay. Well, that's just a trapezoid. Now you can think about it as a trapezoid, or if that's too hard a formula for you to remember, then it's just a triangle plus a rectangle. Okay. But I'm going to do trapezoid because I can remember what the trapezoid formula is. Okay. The area of a trapezoid is 1/2 sum of the bases times the height. Oops, dropped my pen. In this case, base 1 is 1, 2, 3. Oops. Base 2 is 1, 2, 3, 4, 5, 6, 7. And the height is 2. Now, if that's hard for you to see, all I've done is rotated it down like this. Basically, my height here is 2. This was 3. That was 7. Okay. So the area here becomes, let's see, 10. Half that's 5 times 2 is 10. Okay. And by next lesson, we'll be able to actually use the definition of, or excuse me, the fundamental theorem of calculus to calculate this. And then we could check our answer. But I'm telling you it's right. I'm not sure. I'm pretty sure it's right. Alright, so finally, just another example of using the properties of integrals, but we're taking an algebraic look instead of a graphical look. In this case, I'm giving you the integral of f of x from 1 to 3 is 5, and the integral of f of x from 3 to 6 is 7. And asking you to find a few different integrals here. So the integral of f of x from 1 to 6 is going to be the integral of f of x from 1 to 3 plus the integral of f of x from 3 to 6. So 5 plus 7. which is 12. Okay. The integral of f of x from 3 to 1. Well, remember we said that there was a property that said the negative integral allows me to switch my bounds. Okay. So basically I'm getting -5. Or we could think about that as if the area integrated from left to right of a given interval is 5, then the integral from the right to left is the negative of it. Okay. And that's it. That's it for your introduction to definite integrals, using their properties, looking at things graphically and algebraically. Next time we'll be talking about the fundamental theorem of calculus, total change, and some ideas that are really going to speed us up in our application of integrals.